Welcome to Thermometry Thursdays, where I talk about the laser-based thermometry projects and sensors I'm working on. Today I'm working on, and I'm kind of introducing this thermometry series with a laser-based sensor that I'm working on. It involves using a two-line technique where water vapor, water concentration is the target gas. And so we actually look at two different lines. And what makes them useful for a thermometer is the fact that the peak absorbance of each line will increase or decrease as a function of temperature. But when you make a comparison between the two lines, one will increase with increasing temperature and the other will decrease. And among other more technical details and theoretical details, it becomes a useful thermometer. And it's nice because it's optical. You don't have to come into direct contact with whatever it is or the gas that you're trying to probe. And so it's something I'm planning on implementing for a calibration service where instead of using thermocouples for detecting the temperature of the gas bath that these sensors are in, I'll be using a laser-based sensor for that. Just a lot more precision, accuracy, control over the temperature measurement. It's absolute, intrinsic, so I don't have to, it's calibration free effectively. And so it'd be nice to have on the temperature side so that I can just be a lot more confident around what the temperature of the gas bath is for these calibration services. So I'll go into a little more detail on just how absorption spectroscopy works in the context of this type of sensor, and then also the two-line thermometry technique. And then as the weeks go on, you'll get to see me build out the sensor. Okay, so I wanted to just kind of walk through the kind of classic setup of absorption spectroscopy. Here's a laser inside a fixture, buried in there. So just when it turns on, laser will emit. And classic example of absorption spectroscopy setup or experiment is you pitch the laser across a cell. There's some windows here that are mid-infrared transparent. Goes across a cell, hits a detector, something like this Redwood Labs detector. And so typically, something typical that the laser might do in terms of, let's call this emitted power and then time. So it may look something like triangular waveform. So if you were to look at the detector and power, look at the intensity on the detector, you could also think about this as voltage on the detector. It might look something like that. And so if we were to purge this gas cell with nitrogen, a non-absorbing gas, or a vacuum, you may see something like this. As the laser is being tuned in current, so it's ramping up in current, the emitted power goes up. But the interesting thing about these tunable diode lasers is that if we look at one period here, let me kind of maybe zoom in. So let's just kind of look at the ramp up. You're going to have lambda, emitted wavelength, and then out here you're going to have lambda plus some delta lambda. Meaning that the wavelength of the output of the laser is changing with respect to time. And so that's pretty straightforward. And so then what happens is if we then go ahead and fill the chamber with this gas cell with CO2, methane, CO, something that absorbs within this delta to delta lambda range, then you'll actually, as you're scanning in time, that's an attempt at a Voigt-like line shape. Anyway, the intensity of the signal on the detector will actually drop. And the reason it's dropping is it corresponds to the absorbance of the absorption of the photons that are hitting these molecules. And so as a function of wavelength, frequency, time, you're getting a drop in intensity. And so there's the Beer-Lambert relation, which defines so it's a negative natural log of the intensity, the absorbed intensity, over the baseline intensity. And so if you were able to capture this, in the non-absorbing gas, which is I naught, and the transmitted intensity I, you can actually resolve what the absorbance is for any particular gas. So that's the very crude fundamentals of absorption spectroscopy. What's kind of neat about this thermometry approach that I've been referring to is if you have, let's just think again in time. Yep. And so we're just going to call this voltage, detector intensity. So again, we have our baseline intensity, and then this is a two-line thermometry technique, right? So you can think of the laser scanning over two lines of water in this case. So water vapor will absorb at two different intensities, or two different lines. So we'll call it lines of just absorbance, transitions, absorbance features, and that's a whole other video to talk about. But they're essentially these. The line shape is actually, for most purposes, and the purposes of this application, they're Voigt line shapes. I mean, just for the sake of example, think of it as these Gaussian-like waveforms, line shapes. And so let's just call that, we operate a laser, we scan it across two lines, and the temperature is 300 Kelvin. So then, let's say we wanted to, we take another measurement, but now the line shape changes a bit. So everything else is the same, but we now have increase. The only thing that's changed is temperature. So you're going to get different relative intensities of this peak for each of these lines at a different temperature. So let's just call that 400K. And so what's really interesting and helpful from a thermometry standpoint is that you can take the integrated area of these different line shapes, and then this you would do analytically once you collect the data. But you can take the ratios and actually calculate. You can arrive at a temperature of 400 or 300K, and so once you've convinced yourself of this, then you can use this as a thermometer within that range. And depending on the peaks of these lines, you can extend the operation of this thermometry technique to wide ranges. In the paper I published that I'll reference in the video description, I used it in a biomass gasification process and was able to measure the inline temperature of the exhaust stream of this biomass gasifier. So that's the technique that we're planning on using. I'm going to build out a calibration chamber effectively, and because I have this methane sensor that I'm building out, and I need to kind of convince myself that the methane values it's outputting are in fact real. So I'm going to get some gas bottles with known concentrations from air gas, throw the sensor in there, run through some steps of methane concentration, and be able to measure temperature at the same time, and water concentration, if I need to. So those are the fundamentals of laser absorption spectroscopy applied to thermometry around these temperature ranges. And basic setup: you have laser, cell, detector. The way I'm planning on implementing this, I may or may not use a cell. We'll have to see what works out better. But if you have any questions on methane sensing, the gas thermometry technique, CO2 sensing, laser-based, electrochemical, NDIR sensors, let me know. There's a link for a free scoping call in the description. Reach out, we'll get started on your project and start collecting data you can trust.